Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam, and other exams related to physical science. Okay. So today it's a Sunday, so there's a Sunday special. So what I'm going to do is I'm going to uh, discuss particle physics, and I'll try to complete particle physics in Sunday today. Okay. So before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. So let's get started, guys. Okay. It's a Sunday special, so I'm trying to complete particle physics today. Okay. Okay, just let me check. There is some technical issue, guys. Just bear with me a second. Bear with me a second. Okay. Okay. So particle physics. Okay. So first we are going to study that fundamental interactions. Okay. How many types of fundamental interaction? Okay, that we are going to study. Fundamental interaction. Fundamental interaction. Fundamental interactions. Okay. Let me check whether I'm audible or not, then I'll proceed further. Fundamental interaction. Yes, I'm audible, so I'm going to proceed further. Okay. So there are 4 types of fundamental interactions. Okay, which we are going to study. The first one is gravitational interaction, electromagnetic interaction, uh, strong interaction, and weak interaction. Okay, so we'll start with first one is uh, gravitational interaction. Okay. Gravitational interaction. Gravitational interaction. Okay, so so gravitational interaction follows inverse square law. Okay, follows inverse square law. Inverse square law follows inverse square law. Second is always attractive. Okay, always attractive. So this gravitational interaction is always attractive. Okay, basic things. Always attractive, and due to mass. Okay, so due to mass, because there is interaction between mass. Okay, attraction force between mass, that is gravitational attraction force. Okay, and so if there are two mass m1 and m2, okay, the two mass m1 and m2, and which are at distance r. Okay, so gravitational force between them is going to be F equal to g m1 m2 upon r square. Okay, that's why it is inverse square law. Okay, so force is g m1 m2 upon r square. Okay, okay, so next is this this interaction is velocity dependent. Okay, sorry, velocity independent. Doesn't matter, it doesn't depend on velocity. Okay, so velocity independent, independent, velocity independent. Next is orientation independent. Okay, so orientation orientation independent. It doesn't depend on orientation. Okay, how they are oriented. Second is this electromagnetic interaction, guys. Okay, electromagnetic interaction. Electromagnetic interaction. Okay, so electromagnetic interaction is attractive or repulsive. So it may be attractive or repulsive. Okay, attractive oblique repulsive, attractive oblique repulsive. Second is, and this that electromagnetic interaction force is that Coulombic force, right? That is Q1 Q2. F is proportional to Q1 Q2 into R square, or F is equal to K Q1 Q2 upon R square, and where K is dependent on the medium. Okay, that depends on medium, dependent of medium, dependent of medium, dependent of medium. Okay, this is the F. Okay, and this is K. Okay, and this is infinitely large. Okay, this may be infinitely large. Okay, and next point is this electromagnetic interaction, that is okay, that depends on the medium. Okay, that force, electromagnetic force, depends on the medium and velocity. Okay, dependent on medium and velocity. Okay, so electromagnetic the interaction is dependent on medium and velocity. Okay, so the velocity of the particle and the medium, in which medium that particle is. Okay, so this is about electromagnetic interaction. Next is strong interaction, guys. Okay, third is its strong interaction. Strong strong interaction, strong interaction. Okay, so these are, first is short range forces. Okay, so they are short range, short range. They are short range forces. So there are short range forces. Okay, short range force between the particle is there. They are the distance is very short, guys. Okay, so short range, like in nucleons, the force between nucleons, the nuclear force. That okay, that comes in strong interaction. Okay, so short range force, you can write short range force. Next is charge independent. So they are charge independent. Okay, something missing, guys, here. I'm going to write. So this is okay for this fundament. This is the fundamental gravitational interaction, right? For gravitational interaction, guys, the exchange particle is exchange particle. Exchange particle. Exchange particle is graviton, guys. Okay, graviton. Exchange particle is graviton. Important. And for electromagnetic interaction, okay, for electromagnetic interaction, the exchange particle is that photon, okay, exchange particle is photon, and whose energy we know, right, equal to mc square. Very important. Okay, so exchange particle for electromagnetic interaction is photon, and for gravitational interaction is graviton. Okay, now this strong interaction, so this is charge independent. Okay, strong interaction is charge independent, so that doesn't depend on the charge. Okay, that is strong forces, we can say. Okay, and this is uh, velocity dependent. Okay, it's velocity dependent, velocity dependent. So it depends on velocity of particle. Okay, next is uh, spin dependent, spin dependent, spin dependent. Okay, and also isospin dependent, isospin dependent, isospin dependent. Okay, next is nearest neighbor interaction. Okay, nearest nearest neighbor, nearest neighbor, nearest neighbor that interaction. Okay, nearest neighbor interaction, there would be interaction between nearest neighbors. Okay, next is saturation property. So these have saturation property, guys. They are short range forces and they have saturation property. It means strong interaction have saturation property. Okay, saturation property, saturation property, saturation property, saturation property. Okay, saturation property, so they have saturation property, so they get saturated. Okay, and then they are non-central forces. Okay, strong interaction. Okay, non-central forces, they are not central forces, they are non-central, non-central forces, non-central force. Okay, so strong interaction is non-central force, non-central force. Okay, next so strong interaction means they are the strong forces are tensor quantity, so they are tensor quantity. Okay, tensor quantity. Okay, so they are tensor quantity. Okay, so this is about strong interaction, guys. Now next is weak interaction. Okay, also the exchange particle. Okay, exchange particle for strong interaction is exchange particle, exchange particle, exchange particle is exchange particle is, this is gluton and meson, guys. Okay, glue, gluon, gluon. Okay, gluon, and second is meson, gluon and meson. Okay, and this is very strong, guys, very strong, very strong exchange particle. Okay, and this is strong, just as strong. Okay, so exchange particles for strong interactions are gluon and meson, and gluon are very strong and meson are strong. Okay, these are the exchange particles. Okay, Next is weak interaction, guys. Fourth, weak interaction. Weak interaction. Okay. And the example of weak interaction is beta decay. Beta beta decay. Okay. And exchange particle for the weak interaction. Exchange particle. Exchange particle for weak interaction. Exchange particle for weak interaction is gauge boson, guys. Gauge boson. Okay. Gauge gauge boson. Gauge boson. Okay. So this is gauge boson. Gauge boson. Okay. That is the exchange particle. And this is the exchange particle for weak interaction. Okay. So this is about interactions, different types of interaction, guys. Now we'll study elementary particle. Elementary particle. Elementary particles. Okay. So we'll categorize the elementary particle on the basis of spin and on the basis of interaction. Okay. Okay, guys. Well, so now on the basis of spin, okay, elementary particle we are categorizing. Okay, on the basis of spin. Okay, on the basis of spin. So the elementary particles are of two type, guys. Okay, are of two type. The first is fermion. Okay, and the second is boson. Fermion and boson. Okay, fermion means half integral. Okay, this spin is half integral. Okay, spin is half integral. Okay, and for boson the spin is integer. Okay, or integral. Okay, so spin is integer. So this is the classification of elementary particle on the basis of spin. Next, on the basis of interaction. Okay, on the basis of interaction, on the basis of interaction, okay, on the basis of interaction, so we are going to categorize it, or we are going to classify it. Okay, so elementary particle. Okay, so they are strong electromagnetic magnetic and weak. Okay, So elementary particle are strong, electromagnetic and weak. Okay, the interaction is strong, electromagnetic and weak. So for strong and electromagnetic case, there is a hadron, guys. Okay, hadron. Hadron. And for electromagnetic and weak, the elementary particle is lepton. So leptons are weak and electromagnetic. Okay, and and for strong and electromagnetic, so there are hadron, guys. Okay, I'll classify that as well. So now I'm going to classify the elementary particles. Okay, so elementary particle, elementary particles. Okay, so hadrons are yeah, made of that strong and electromagnetic. Okay, so elementary particles. So this chart, I'm going to make a chart which is very important, guys. Okay, so you need to note down and memorize this chart for solving questions, guys. Okay, so very important chart which I'm going to make it. I will classify the elementary particle. Okay, this is lepton, guys. Okay, so lepton. Okay, and then this is going to be hadron. This is going to be hadron. Okay, elementary particle. So lepton and hadron. Okay, so leptons are, I'm going to write lepton. What are lepton? Okay, leptons are electron tau. Okay, tau minus and mu minus. Okay, muon. This is muon. This is muon. This is tau. And this is electron, we know, right? And so the antiparticles of antiparticle of electron is E positive, tau is tau positive, and mu is mu positive. Okay, these are antiparticles. And there are neutrino. Okay, neutrino are also leptons. So neutrinos are like mu e, mu, and nu tau. Okay, these are neutrino. And antiparticles, so it's their antiparticles are there also. Antiparticles are this one. Antiparticles are denoted by bar. Okay, so mu e bar, this is antiparticle, and mu bar and nu tau bar. So these are antiparticles. These are lepton, guys. You need to note down and memorize, guys. Okay, because by this chart you will be able to solve all the questions, okay, of particle physics. This chart is very important. Next, the hadron. Hadrons are of two type, guys. Okay, meson and baryon. Okay, baryon. Meson is also, we can say this meson is boson. Okay, boson. Mesons are boson, and baryons are fermion. Okay, so hadrons are categorized into two parts, that is meson and baryon. Okay, and in meson the particles are pi positive. Okay, pi positive, pi 0 the pion. Okay, these are pion. Okay, pi negative. Okay, and then cation, this is k positive and k not, k to the power 0. Okay, and then eta 0. So these are meson or boson, guys. Okay, and baryon, that is fermion. Okay, they are further classified into two parts. First is nucleon. Okay, nucleons are of two types, right? that is we know, that is neutron and proton, right? And now second is baryon is second is hyperon, guys. Okay, hyperon, hyperon. This chart is very important. Hyperon. Hyperons are this is sigma plus, sigma 0 and sigma minus. Okay, this is sigma. Second is cascade. Okay, E negative and this cascade, this is cascade. Okay, E naught, E negative and E naught, and then this is omega negative. Okay, omega negative, and third is lambda naught. Okay, so so this is sigma. Okay, these are cascade. Okay, this is omega and this is lambda. Okay, this chart is very important, guys. I would request you, please memorize this chart. Okay, very important chart. By that if you know this chart, you can easily solve further questions. Okay, and particle physics is going to be very easy for you then. Okay, so very important chart, so you should know it. So these are hyperon, guys. Okay, cascade, sigma, omega, lambda. Okay, this is lambda 0, omega minus, cascade E minus, E 0. This is lambda 3. This is lambda plus, lambda naught, and lambda minus. Okay, okay, guys. So this is the categorization of or classification of elementary particles: leptons, mesons, and baryons, guys. Okay, these are very important. Okay, well, this is the chart. Next is next is this is now for this pion, right? These are the pions, right? For pion, we'll check the multiplicity. Okay, pion means pi positive, pi negative, and pi naught. Okay, so pi positive, pi negative, and pi naught. Okay, so for this multiplicity is 3, guys, because there are 3 in pion. There are 3 particles, right? Different particles. So that's why the multiplicity is 3. Multiplicity. Okay, now for eta naught, there is only one particle, right? For eta naught, this one eta naught. So multiplicity is going to be 1. Similarly, for omega negative, the multiplicity is 1, right? And for neutron and proton, because they are 2, right? They come in nucleon, right? For neutron and proton, the multiplicity is going to be 2. Okay, similarly for k plus k naught, cation, this one, k plus k naught, right? because in this category there are two particles, right? K plus cation. In cation there are two particles, K plus K negative. So that's why the multiplicity is 2. Similarly for cascade, E negative comma E naught. For this also multiplicity is 2 because in cascade there are two particles. Okay, and if you talk about sigma, there are three particles, right? So for sigma, that is sigma plus, sigma minus, and sigma 0. So multiplicity is 3. Okay, these are the multiplicities of these particles. Okay, now we'll find isospin. Okay, isospin. Isospin is that. Okay, isospin will discuss. And also strong interaction means, strong interaction means strong interaction. Strong interaction means charge independent, right? I have already explained. Charge independent. Yeah, strong interaction is charge independent, right? So we can't distinguish because in strong interaction the is charge independent. That's why. So we can't. So we can't distinguish. We can't distinguish N and P. Okay, because both having same mass. Proton and neutron have the same mass. Okay, so strong interaction means because it's a charge independent, right? It doesn't depend on the charge, right? So both having the same mass, right? Okay, so independent, so we can't distinguish neutron and proton. Okay, because both having the same mass in strong interaction. Okay, in strong interaction. Okay, okay, so this is the so now I will talk about. So that's why isospin for N and P is same. Okay, so now isospin is denoted by I. Okay, and this value is mod of I1 plus I2. Okay, to mod of I1 minus I2. Mod of I1 plus I2 to mod of I1 minus I2. Okay, and now we'll find this third component of isospin, right? This is noted by I3. I3 is very important. Okay, in particle physics. Third component of isospin. Third component of isospin. Okay, that I3 is going to be, we'll find value of I, right? And after that I3 is going to be minus I to I, minus I2 plus I. Very important. Okay, this is important. Okay, well, so this is the spin and isospin. And multiplicity is going to be, we'll find different isospin for different identical particles, different elementary particles. Okay, then it will be more clearer to you. So multiplicity is 2I plus 1. Okay, so this is the I. So multiplicity formula is 2I plus 1. Okay, now first is, so now if you talk about nucleon, so if you talk about nucleon, right, which is doublet, guys. Okay, which is doublet. because there are N and P. That's why I told you guys you need to note down and memorize this chart. Okay, here you can see, if you talk about nucleon, there are two, neutron and proton. If you talk about in meson, right, the pion has three multiplicity, right? Cation has two particles. The eta has only one particle, eta naught. Similarly, if it here in baryon part, you can see sigma has three particles, three elementary particles. Cascade has two particles. Omega has only one particle. Lambda has one particle. Okay, so that's why. So if you talk about nucleon, so it is doublet because it has two particles, in nucleon. In nucleon, there are two particles in nucleon. Okay, neutron and proton. Okay, so here for nucleon is doublet, right? So multiplicity is going to be 2i plus 1, that is multiplicity is 2, right? I have told you how to get multiplicity, right, for nucleon. So that's why I told you this chart is very important, guys. Okay, then if you know this chart, you can easily identify all the particles and their categorization. Okay, and how many particles are there. But if you talk about pion, there are three particles. If you talk about cation, there are two particles. If you talk about sigma, there are three particles, means multiplicity is sigma. And this formula is very important, that is this one, multiplicity equal to 2i plus 1. If we know this, then we can easily find out the value of isospin, right? Isospin. So 2i plus 1, for if we talk about nucleon, it's a doublet. There are two particles and elementary particles, right? So 2i plus 1 equal to 2. So from here, 2i is going to be 1. Okay, and value of I is going to be 1 by 2. So isospin is 1. Okay, so here, because they have same mass, right? So we can't distinguish them. So isospin is same. Okay, I is half. And now we'll find I3, third component of isospin, right? I3 is going to be minus I2 plus I, right? So this is, so I3 is going to be, because there are two particles, so minus I2 means this is minus half and 1 half, right? So this implies for proton, the third component for proton, I3 is 1 by 2, and for neutron, I3 is minus 1 by 2. But for proton and neutron both, I is 1 by 2. Okay, very important, guys. This one. Okay. Okay, so next. Okay, so this is important. Next is next for okay, this is one. Now for pion we are going to solve. Okay, for pion, if you talk about pion, second is pion. Pion has the three particles, right? That is pi plus, pi minus, and this. Okay, pions are pi plus, comma pi naught, comma pi minus. So these are pion, means pion has triplet, right? Like there's a nucleon doublet, right? That there are two particles. Similarly, in pion category there are three particles, right? This chart I'm showing you again and again because it's important. Pion 3. Okay. So for pion, this is three particles. So this means this is called triplet. So now we have formula, the multiplicity equal to 2i plus 1. So it means 2i plus 1 is multiplicity for pion is 3, right? Multiplicity for pion is 3, so this means 2i is going to be 2, right? Because 1 will go in right hand side, so I value is 1. I value is 1 means I3 we know, right? So third component of I3 is minus I2 plus I, right? Minus I2 plus I. So I is 1. So minus I. So then I3 are going to be I3 is going to be I3 is going to be minus 1 comma 0 comma 1, right? So I3 is this. And now we'll find for now for this one, for I and I3 component, for pi plus is going to be 1, pi not, and pi minus. Okay, so isospins are same, that is 1 1 1, right? But this one I3 component for pi plus is plus 1, guys. Okay, and for pi 0 is 0, and for pi minus is minus 1. Okay, so these are the values of isospin and spin for pion. Okay, well, so this is the one. Next is third, for eta naught. For eta naught, this is singlet, right? So for that you need to check the chart, guys. That's why I made a chart first. Okay, we talk about eta naught. This is singlet, only one. Okay, there is one. So multiplicity is going to be 1. So for eta is singlet. So this means 2i plus 1. That multiplicity is 2i plus 1 is 1. Okay, so from here 1 1 will get cancelled, right? 2i is going to be 0, implies I equal to 0, right? And that implies I3 is also going to be 0. Okay, because this is 0. So for eta naught, I equal to 0 and I3 equal to also 0. Okay, so now we are going to study Gell-Mann-Nishijima relation. Okay, this is Gell-Mann-Nishijima Gell-Mann-Nishijima relation. Okay, Gell-Mann-Nishijima relation. Okay, Gell-Mann-Nishijima relation, and so that is, guys, this is Q equal to I3 plus B by 2. Okay, this is the Gell-Mann-Nishijima relation. Okay, where B is baryon number, guys. Okay, where B is baryon number. Okay, so now we'll by this formula, okay, we'll get the isospin and we'll get the charge. Okay, let's see is this relation is valid or not. Okay, or is there some modification needed, okay, for this formula which is given by Gell-Mann-Nishijima. Okay, well, so now I'll make a chart for this. Okay, so I3, B and Q. Okay, and now we'll check for pion plus, pion negative, pion 0, proton, neutron, and lambda naught. Okay, so for pion we know that I is 1. I have already found, right? And this is I3 is 1 for pi plus. Okay, so baryon numbers, the baryon number is 0. How? because that's why I'm saying this chart is very important. So this is baryon, guys. So these are baryons, guys. If you get any one of these, right, so then baryon number is going to be 1. If there are other elementary particle apart from these, then they are not baryon. Okay, so this is baryon. So these are the baryon. If you get any particle of this, then baryon number is going to be 1. Okay, so this is going to be, 0 0 1, right? So this one is similarly for it, 1 -1 0 and -1. The charge is 1. Baryon number is 0. The baryon, okay. I is 1 and I3 is this. For pi 0, we know isospin is 1 and this value is 0. I have already found, right? Baryon, because it doesn't come in baryon category, it comes in mason category, right? So baryon number 0 and charge is 0, guys. For proton, if you talk about isospin is 1, that we know, and I3 I have found, that is plus half, and baryon is, it comes in baryon means 1 and charge is 0. For neutron, if you talk about, and we are finding this charge by this formula, guys. Okay, I'll show you the Nishijima formula. Okay, this one, Q equal to I3 plus V by 2. So this is Gelman Nishijima formula, right? Okay, so for neutron, the charge is plus for this. Okay, plus 1, because if you put this formula, this here, right, this is going to give 1. If you talk about neutron, right, neutron isospin is 1, I3 is minus half, baryon number is 1, and if you talk about charge is 0. This is correct. But if we talk about this lambda, guys, okay, lambda naught, I is, we know, 0, I3 is 0 because only one particle, and baryon number is 1 because it comes in baryon category, right? I'll show you lambda naught. Chart is important. This is in baryon category it comes. Okay, baryon category, this baryon hyperon, right? This lambda. So so this charge is, but if we use this formula, guys, here, right, I3, you can see here, look at here, right? If you see this formula, q we have to find, q is going to be, I3 is 0 for lambda naught I'm talking about, and v is 1. So this is 1 by 2. So we can see value of q is giving 1 by 2. Charge is 1 by 2 here, guys. Okay, charge is 1 by 2, 1 by 2. Okay, and we know that this is not possible because the charge is 0, right? Not possible. So this means this formula, that is Gelman-Nishijima formula, is not valid for this particle. Means there needs to be some modification in this formula, guys. Okay, so this is the not possible for it, right? Well, it means not possible. Formula is invalid. Okay, formula is invalid. Formula is invalid. Okay, so now there needs to be some modification in this formula. Okay, so next, uh, before that, I'll explain this one. Strangeness. Okay, strangeness. Strangeness is strangeness is denoted by S. Okay, strangeness. Okay, so there are some particles. What are the strange particle? I'm giving you the definition of strange particle, and that is called strangeness. Okay, okay. So this one, there are some particle. There are some particle. There are some particles. There are some particles in nature there are some particles there are some particles in nature that are that are created by strong interaction. Okay, strong. So there are some particles in nature that are created by strong interaction, but but decayed but decayed via they decayed via weak interaction. Okay, weak interaction. So there are some particles in nature that are created by strong interaction but decayed via weak interaction. Okay, so those particles are called strange particle. Okay, those particles are strange particles. That is called strangeness. Okay, those particles are strange particles. Those particles are strange particles. Okay. Okay. Now, so we have modified this Gell-Mann-Nishijima formula, guys, because there are strange particles as well, right? So why we haven't got the correct answer? So the charge of lambda zero, that lambda zero should be zero here, but by this formula we have got charge. We have got just that 1/2 charge, right? Because this particle is strange particle. This particle is made of created by strong interaction, but this decays in via this decays via weak interaction, right? So that's why because they are strange particle, that's why they are not giving the correct answer, right? That's why the different charge. So this means we need the modification in Gell-Mann-Nishijima formula, and then that formula is modified and given this formula. So the formula is Q equal to I3 plus B plus S by 2. This is the by this formula, this is the modified formula, and by this formula you can get charges of all the elementary particles. Okay, so this is valid for all the particles. Okay, so this is modified form of modified this is modified form of modified form of Gell-Mann modified form of Gell-Mann Nishijima modified form of Gell-Mann-Nishijima relation. So modified form of Gell-Mann-Nishijima relation. Okay, so this is valid for everything. Okay, all the particles. Now we'll find. Okay, and because it's a strange particle, that's why this is not part of not valid. Okay, so this is the modified form of Gell-Mann-Nishijima relation. Okay, so now we'll find for pion. Number one, for pion, right? That is for pions, that is pi plus. For pi plus, if you talk about pi plus, I is going to be 1, right? And I3 is 1. I have already found, right? And the pion is comes in mass on, right? So that means baryon number is 0, because that doesn't come in uh, baryon, right? That is the part of mason. Okay, so B is 0. And strangeness, so we'll find the strangeness of it. Okay, so then Q by formula, Gell-Mann-Nishijima formula, Q equal to I3 plus P plus S by 2, right? So now we can, so because it's very important formula, guys, by that you can you can easily find strangeness, because you cannot remember or memorize all the strangeness of all the particles, right? So by this formula yeah, you can easily find out any particle's strangeness by putting the values. Okay, you just need to know that chart which I have explained, and I3 you can find out. Okay, charge you can see, so charge you can easily find out, so you can easily find out the strangeness. So this formula is very important for getting strangeness. So you need to note down and practice questions. Okay, so Q is going to be Q. So pi plus means charge is 1. Okay, plus 1. right? Equal to I3 is 1 plus B value is 0 plus S by 2. Now we are getting the strangeness of this particle, okay? 1 will get cancelled, guys, okay? So S by 2 is going to be 0. That implies value of S is going to be 0. So for pi plus, the strangeness is 0. So if we have to find the strangeness for pi plus, by this formula we'll find it, and that value is 0. S equal to 0 for pi plus. If S equal to 0 for pi plus, then the particles, the remaining particles in pion category, that is pion plus, pi plus, pi minus, and pi 0, for them is also, this is S strange is S is 0. It means this pion is not a strange particle, okay? It's a meson. Okay, guys, next. Next is similarly we'll find for second, for cation, right? Cation has two particles, okay? So in cation we are going to find K plus, the strangeness of K plus, okay? So you will use the formula for cation. We know that for cation I is, you can easily find out for cation, right? If you don't know, cation has two particles, K plus and K minus. In the chart I'll show you this one. I'm showing you again and again, it's important, right? This is the cation, two particles, so multiplicity 2 means 2I plus 1 equal to 2. You can easily find out I value, and then I3 value like this, okay? Okay. So this is going to be, this is K plus, okay? This is K plus. So K plus I will find first I. So we know the formula, right? Q equal to, we are using Gell-Mann-Nishijima formula, modified Gell-Mann-Nishijima formula for getting the strangeness for K plus, okay? This is I3 plus B plus S by 2, right? Q is for this plus 1 equal to I3 value for this is 1 by 2, guys, okay? Plus B, it is not baryon, okay? So this is 0 plus S by 2, okay? So cation will check it, okay? So this is going to be, this will come here, right? So S by 2 is going to be 1 by 2. 2 will get cancelled. It means S equal to 1. So for cation, S is 1. It means it is a strange particle, and whose strangeness is 1. Okay. Next, for the third one is for eta naught. You can find out similarly that Q is 0 for eta naught, equal to I is 0 for it, okay? 0 plus B, it's not baryon, 0 plus S by 2, right? So for this, S is going to be 0, means for eta naught, S is 0, okay? Similarly, for neutron and proton, right? Neutron and proton, we have a formula, right? Q equal to I3, write this formula again and again, okay? Because then you will learn it quickly. I3 plus B plus S by 2, right? So Q for neutron is, so if we talk about proton 1, okay? And okay, we are going to find for proton, okay? So for first proton charge is 1, right? I3 is 1 by 2, my apology, and it's not, it's a baryon, so 1 plus S by 2, right? So this is going to be 1 equal to 1 by 2 plus 1 by 2 plus S by 2, right? This will get cancelled, so S by 2 equal to 0 implies S equal to 0. So for proton, strangeness is 0. Similarly, we'll find for neutron. For neutron, the Q is 0, right? Charge is 0, equal to I3. This is minus 1 by 2 for neutron, right? And plus 1 by 2 plus S by 2. I mean to say, you can write like this. Baryon, it's a baryon, right? So 1 plus 1 plus S by 2, right? So this 1 will get cancelled, so this is going to be 0 equal to minus 1 by 2 plus 1 by 2 plus S by 2, right? This will get cancelled, that means S equal to 0. So for a nucleon, strangeness is 0, so they are not a strange particle. Okay, next is this one, guys. For this one is fourth, right? Next for fifth. So this is for fifth is sigma plus, means this sigma plus, right? We'll find Q equal to I3 plus B plus S by 2, right? Strangeness we are finding. Charge is 1 plus 1 equal to I3 for it is this one is half. No, this is 1, guys, for this. Okay, 1 plus B is this is baryon, right? 1 plus S by 2. 1 will get cancelled. Okay, so this is going to be S by 2 is going to be minus half. So S is going to be minus 1. Okay, similarly sixth we have to find for cascade 1. So cascade 1, right? Formula is same, Q. This is minus 1 charge. I3 for cascade 1 is 1 by 2. 1 by 2. Okay. Cascade is I3 minus 1 by 2, right? Okay. I3 minus 1 by 2 plus it's a baryon, so 1 plus S by 2, right? So minus 1 equal to minus half plus half plus S by 2. This will get cancelled. So implies S value of S equal to minus 2. Okay. So cascade strangeness is minus 2. So this is a strange particle. Next, 8th, 7th, okay, for omega minus, right? I'm solving it because after some after some time we should know these values, right? If you don't know, we can use formula and find out, because that is needed when we solve the question. Okay. Well, next is this one. Okay, so omega minus is going to be this one. For omega minus 1, I'm directly writing. Okay, Q equal to minus 1. I3 for omega is 0 plus baryon, it's a baryon, so 1 plus S by 2. So from here, S by 2 equal to minus 1 minus half, right? So this is minus 3 by 2. 2 will get cancelled, implies value of S equal to minus 3. So for omega 1, omega minus, strangeness is 3, minus 3. Similarly, 8th one for lambda naught. If we talk about lambda naught, Q is going to be I3 plus B plus S by 2. Okay, this is going to be 0 equal to 0 plus 1 plus S by 2, right? So that implies S by 2 value is going to be so from here you can get the value of S by 2 equal to minus half, right? So that implies value of S equal to minus 1. So for lambda naught, it's minus 1. Okay, this is the one. Next, guys. So next, so these are the strangeness, and I'm going to write it here also. So for K plus, okay, strangeness is 1. Okay, for lambda plus, strangeness is minus 1. For lambda minus, strangeness is, okay, so strangeness will be different for different because in lambda, sorry, sigma has three particles, right? Sigma plus, sigma minus, sigma naught. So for these three, strangeness will be different, guys. Okay, so this is -1. My apologies for lambda, but for sigma minus, strangeness is uh, -2. So you can find out by formula, guys. Okay, now I'm writing directly. And for omega inverse, the S is -3, which we have found. Okay, and right, for lambda naught, S is -1. Okay, this also you should know. So now you know how to find strangeness. Okay, you just need to note this formula, modified form of Gelman-Nishijima formula. So that is Q equal to I3 plus B plus S by 2. Okay, B plus S by 2. Okay, so next is this, I'm talking about this conservation. Okay, okay, just give me 1 second, guys. Okay, okay, guys, thank you. Next is we'll find the lepton number. Okay, and also for exact, so I'm going to explain something, right? This is important. So conservation law. Okay, I'm not writing much for this. Okay, I'll just explain conservation law. Okay, so conservation law, right? So there is approximate and exact. Okay, approximate means the reaction may or may not be allowed. Okay, and is exact means if these conservation laws are followed, okay, then reaction is not allowed in the nature. Okay, if these, I'll tell you those laws. Okay, okay, I'll tell you, that would be better. Okay, for any reaction to be allowed or happening, or for finding any reaction, right, which is electromagnetic, uh, weak interaction, or which is made by strong interaction. So we need to check those conservation. Okay, so energy should be conserved. Okay, and angular momentum should be conserved. Okay, linear momentum should be conserved. Okay, and this, and baryon number should be conserved, lepton number should be conserved, isospin should be conserved, I3, the component of I3 should be conserved, right? Charge conservation. Okay, CPT, charge parity conservation. So what I'll do is I will explain that when I will solve questions, so that will be better, guys. Okay, so next we are going to, then you can easily understand that. So now it is lepton number, guys. We are going to lepton number. Okay, lepton number. So LE. Okay, these are lepton, guys. I'll show you this chart. Chart is important. I told you, very very important. Okay, most important. This is the chart, guys. Okay, so these are leptons, guys. Okay, if we are talking about electron, so we can write Le, that is lepton. Okay, Le. If we are talking about muon, then we will write then we will write uh, L mu. Okay, if you are talking about tau, then we'll write tau, L tau. Okay, these are lepton number. Okay, so these are antiparticles. So now I'll explain this. Just give me 1 second, guys. Okay. Okay, guys. So, so now for lepton number we are going to discuss. Okay, lepton number. So this is if LEU I'm talking about. So I'm talking about electron. Okay, LE, lepton number. If this LE is given, then lepton number equal to lepton number will be +1. Okay, LE means lepton number for electron category we are talking about. Okay, so lepton number will be 1 or +1 for electron and neutrino, that is neutrino of electron neutrino. Okay, nu E. Okay, and lepton number is going to be -1 for antiparticle of electron, that is E plus, and antiparticle of neutrino, that is nu E bar, right? And this lepton number is going to be 0 for others. Apart from others, lepton number is going to be 0. When I will solve question, then I will explain how lepton number is conserved, how baryon number is conserved, right? This is important. Okay, but as of now you need to know what is how to get lepton number. Okay, so for electron and neutrino, lepton number is 1. For antiparticle of electron and antineutron, lepton number is -1. For others, lepton number is going to be 0 because they will not come in the lepton category, right? Next is for now L mu. This is also lepton, right? So this value is going to be 1 for muon, means mu minus, and it's neutrino. Neutrino is nu mu. Okay, not far. And this value is going to be -1 for antiparticle of nu, that is nu plus, and comma for antiparticle of neutrino, that is nu bar, and this value is going to be 0 for others. Okay, others. Similarly, I'll write here. Similarly, for L tau, this is also lepton, right? We're talking about tau. This lepton number is going to the value of lepton number is going to be 1 for tau minus and its neutrino, right? This is nu tau, and this value is going to be -1 for tau plus antiparticle and antineutrino. This is tau. This is tau. Okay, this is tau bar. Okay, and this value is going to be 0 for others. Okay, this is important thing, guys. Okay, next is next is baryon number, guys. Okay, baryon number. Okay, so baryon number is denoted by B, and that is +1 for all baryons, guys. For all baryons. For all baryons. For all baryons. Baryons. Okay, for all baryons, and this value is going to be -1 for all antibaryons. For all antibaryons. Antibaryons. antibaryons, okay, and this value is going to be 0 for others, okay, apart from baryons and antibaryons, okay. So all baryons means this chart is important, guys, okay. I'm showing you this again, this one. So these are the baryons, guys, right? And if these are baryons and the baryon number is, if we get any one particle of these one, right, then the baryon number is going to be 1. And if there are antiparticles of these baryon, then the baryon number is going to be -1. For other particle, for these particles, the baryon number B is going to be 0, okay. I hope, guys, you have understood it, okay. Next, this is baryon number, okay. Next is I'll tell you about particle and antiparticles, okay. I'll make a chart so that it will be easy for you to understand. Particles and antiparticles. Particles and antiparticles, okay. Particles and antiparticles. So this is if you talk about mass of particle of mass for particle and antiparticle is going to be equal, guys, okay. If you talk about spin for particle and its antiparticle is going to be the same, okay. If you talk about charge is going to be for particle, if it is plus minus, it is going to be minus plus, means if a particle has charge plus, then its antiparticle has charge minus. If particle has charge minus, then its antiparticle has charge plus, okay. And then I3I, so I means isospin, okay. Isospin for particle and antiparticles are same. I have already explained that, right? Isospin and isospin, right? So for particle and antiparticle means if you talk about this one electron, right, it's a particle. So isospin and that spin, that isospin going to be same for electron, right? If you talk about any baryon particle, right, this I, that is isospin, is going to be same baryon particle and antibaryon particle, okay. And similarly for meson and anti-meson particle, right? Next is strangeness, guys, strangeness. Okay, before that I'll talk about this one, uh, magnetic moment, okay. Magnetic moment, magnetic moment is going to be same in magnetic, same in magnitude, same in magnitude, and opposite in the sign, opposite in sign, okay. So magnetic moment, if you talk about, so if we talk about magnetic moment of particle and antiparticle, so that is going to be same in magnitude. In magnitude it will be same, but and opposite in sign, but their sign will be different, okay. Similarly, if you talk about I3, the I3 means third component of third component of isospin, right? This applies for the same. So this is going to be same in magnitude, okay, but opposite in the sign. So this is the isospin for particle and antiparticle, okay. If you talk about strangeness, strangeness so that is going to be same in the magnitude, strangeness, okay, for particle and antiparticle. Strangeness is going to be a very important thing, guys, okay. Strangeness is going to be same, okay, in magnitude, but but their sign will be different, okay, or their sign will be opposite, okay. Now this is the strangeness, guys, okay. Now if we talk about hypercharge, Hypercharge is also, I'll explain what is hypercharge. Okay, hypercharge will also be same in magnitude, okay, and opposite in the sign. Okay, so magnetic moment, third component of isospin, strangeness and hypercharge, if we talk about those things, so they are going to be same in magnitude, okay, but opposite in sign. Okay, okay guys, next. So hypercharge is, I'll tell you what is hypercharge. Hypercharge y equal to, this is denoted by y equal to s plus b. Strangeness plus baryon number is called hypercharge. Okay, so this is hypercharge. Hypercharge. This is hypercharge. Okay. Now conservation laws, guys. Okay. Right. I'll make a chart. Conservation law. Conservation law. Conservation law. Okay. Conservation law. This is conservation law, right? Okay. So it is very important chart, guys, which I'm going to make. Okay. So strong electromagnetic interaction and weak interaction. Okay. Weak interaction. EM. Okay. So if you talk about energy, guys, okay, just wait. Strong, EM, and weak. Okay. So if you talk about energy, guys, energy for strong energy should be, for energy electromagnetic, and for weak this energy must be conserved. Okay. For strong interaction to if means reaction uh, to happen by strong interaction, to happen by electromagnetic interaction, to happen by weak interaction. Okay. Now momentum, that is momentum, energy momentum for this should be conserved. Okay, I'll explain. For angular momentum, angular momentum, angular momentum, angular momentum, for angular momentum will should be conserved for strong interaction, weak interaction, and electromagnetic interaction. Okay, charge charge should be conserved for strong electromagnetic and weak all. Okay, and baryon number should be conserved for these three interactions. Okay, lepton number should be conserved for these three interactions. Okay, isospin, now I'm writing right because these should be conserved. Okay, if you talk about isospin, okay, for isospin, for strong it should be conserved. Okay, for electromagnetic it shouldn't be conserved. Okay, and for weak it shouldn't be conserved. Okay, if you talk about that this I3 component, okay, I3 component, that third component of isospin, this should be conserved, this also should be conserved, and this shouldn't be conserved. Okay, if you talk about strangeness, I'm writing by S. The delta S for strong interaction should be 0, for delta S here should be 0, or for this, for weak, delta S should be 0 plus minus 1. If you talk about parity, parity, this should be conserved, this should be conserved, and this should not be conserved. This chart is very important for reaction to identify whether this is made of strong interaction, electromagnetic interaction, or weak interaction. I will solve question, then it is going to be more clearer to you. Okay, uh, but as of now, I would like to inform you this one, right? So these all are conserved for all these. Okay, for you, what you need to understand for strong, if any reaction is created or done by strong interaction, then everything should be conserved. Okay, baryon number, charge number, isospin I3, and S and delta S value should be 0. Okay, for strong interactions, we'll check one by one. We'll check energy, momentum, charge, baryon number, isospin, everything will check. Okay, and if all are conserved and delta S value is 0, then that reaction is made of strong interaction. If we check the we check the that reaction. Okay, and if these all are conserved, but only isospin is not conserved. Okay, if only isospin is not conserved, then and delta S equal to 0, then that reaction is made of electromagnetic interaction. If we talk about weak interaction, this is very important. So we need to identify in electron whether it is made of strong interaction, electromagnetic interaction, and weak interaction. Okay, these are 5 marks questions, guys. Okay, so here if we talk about weak interaction, isospin and I3 component shouldn't be conserved, right? These shouldn't be conserved. Okay, and delta S should be 0 or plus minus 1, either 0 or plus minus 1, or parity also shouldn't be conserved. Okay, 0 and plus minus 1. Okay, plus minus 1, plus minus 1. Okay, so this is very important chart. So when we solve question, this chart is going to be used. So this chart you must note down and memorize it, guys. Next. Next is, okay, this is next is going to be that resonance baryon, guys. Okay, resonance baryon. Resonance baryon. Resonance baryon. Okay, so this is what are resonance baryons. Okay, baryon we know, so there are resonance baryon. Okay, so this is there are four particles which are called resonance baryon: delta plus plus, delta plus, delta naught. Okay, delta naught, and delta minus. So these four are resonance. These four are called resonance baryon. Okay, and for that, because in this particle category there are four particles, right? Means their multiplicity is going to be 4. It means 2i plus 2, 2i plus 1 is going to be 4. 2i plus 1 is going to be 4. 2i plus 1 is multiplicity, right? So now from here 2i is going to be 3. That implies value of I is going to be 3 by 2, right? Now what we are going to find? Now we'll find I3, right? I3 we know I3 means mod of this I3 means minus I2 plus I, right? This formula I have already explained. So for I3 is going to be I3 for delta plus plus is going to be 3 by 2. Okay, you need to note down I3 for delta plus is going to be 1 by 2. Okay, and I3 for delta naught, I3 for delta naught is going to be minus half, and I3 for delta minus is going to be minus 3 by 2, because values are minus 1, minus I2 plus I. Okay, so these are the I3 values of delta plus plus, delta plus, delta not, delta minus. Okay, and now we can easily find out strangeness as well. We have a formula, right? That is modified form of Gelman-Nishijima formula, right? That is Q equal to I3 plus B plus S by 2. Okay, this we know, I3, right? So from here, this is the Q value, right? So we are going to find for delta plus plus, right? For delta plus plus, this is going to be 2 equal to I3 value. We have already find this 3 by 2, 3 by 2 plus it's a baryon. Yes, it's a baryon because it's a resonance baryon, but it comes in baryon. Okay, so 1 plus S by 2. So this is going to be 2 into 3 by 2 plus 1 by 2 plus S, right? So from here, this 3 by 2 plus 1 by 2 is 2. This will get cancelled, right? Because this total is 2, right? So S by 2 is going to be 0. That implies value of S equal to 0. So for delta plus, strangeness is 0, guys. Similarly, you can find for delta plus, delta naught, and delta minus. Now I'm going to tell you one trick, guys, which is very important for solving the question. Okay, this is important. Okay, if in any reaction you see gamma, okay, that is gamma photon, and if gamma photon, and if allowed, if reaction is allowed, okay, then by EMM, if you see gamma, then that if reaction is allowed, then it is by EM interaction, guys. Gamma means EM interaction. Okay, this is a trick. Okay, interaction, EM interaction. Okay, similarly, if you found mu v, that is neutrino, any neutrino oblique anti-neutrino, any anti-neutrino, right? And if allowed, if reaction is allowed, then this is by weak interaction, guys. Okay, this is by weak interaction. So you see, if you see the reaction, if you find these values, then you can easily find out that this is a electromagnetic, this is made by electromagnetic reaction, electromagnetic interaction, or weak interaction. Okay, so by weak interaction, okay. Well, this is the one. This is very important trick, guys. You need to note down. Okay, now we are going to solve one question. Okay, question is, we have omega minus, right? This we know, this is a category of baryon, right? And we need to find and S. I and S point we need to find, right? I means there is only one particle, right? So 2I plus 1 is equal to 1. So from here 1 will get cancelled. 2I is going to be 0. So implies I value is going to be 0. Right? Now S, we know formula, that is a modified form of Gelman-Nishijima formula, right? So that is Q equal to I3 plus B plus S by 2. This is a baryon, right? So Q charge is minus 1 equal to I3 is also, that implies I3 is also 0, right? So 0 plus, this is a baryon, so 1 plus S by 2. So this is going to be S by 2 is going to be minus 2. So that implies S is going to be minus 1. Okay, is there any issue? Okay, this is minus 1. Hmm. 2 will go here, right? So this is calculation mistake. Okay, so this is going to be like 1 plus s equal to minus 2, and value of s is going to be minus 3. So strangeness for omega minus is minus 3. Okay, this is the answer. Okay, now next question, guys. Next question is, okay, next question is this one. Okay, we have given reaction. This is n equal to p plus E minus and mu. Okay, so we need to find where that it is made of weak interaction, strong interaction, or weak that electromagnetic interaction. Okay, so by trick we can easily solve it. The trick is here: if mu e and mu minus e, mu e or mu e bar, right, and given you know, if reaction is allowed, then by weak interaction. Okay, so this is by weak interaction. But now I'm going to solve it with proper method. But trick is very important. You need to note down, because if you know the trick, you can easily solve questions quickly in the examination. Okay, I'm going to solve it. So we'll check first in this reaction, that is baryon number. Okay, what we need to check is baryon number. Okay, we'll check baryon number first. It is baryon, right? 1, and this is p plus, right? So p plus means it's a baryon proton, right? And it is lepton means 0. Baryon number is 0 and this is 0. So this is conserved. We can say left hand side equal to right hand side. Now we'll check. Okay, first we'll check. Okay, first we are going to check charge, right? Okay, so now I'm going to check charge. Charge for Newton is 0. Charge for proton is 1. Electron is minus 1, and for neutrino it's 0, right? This is conserved. 0 0, right? Now we'll check lepton number. So it's a electron, so lepton number Le will check first. Okay, Le, it's not a lepton, right? 0. So it's a meson, so it's a 0. It is lepton, it is 1. Okay, electron 1, and this is antiparticle, right? So for mu e neutrino, the lepton number is 1, right? So this is going to be minus 1, so 0, right? This is also lepton number is conserved. Now we'll find anti-neutrino, right? That I, we're going to find I for isospin for neutron is half, for proton is half, right? For electron, isospin is 0. Okay, for electron, isospin is 0. Okay, and because this is only one particle, right? Electron, so 2I plus 1 equal to multiplicity is 1. 1 will get cancelled. I is going to be 0, right? That's why E is 0, and for neutrino it is also 0. Right? This is conserved. Oh, this is conserved. Okay. Now we'll find I3. I3, you can see this is I3. This is minus 1 by 2 I3. We know, right? For neutron, and this is for this it is proton. Proton 1 by 2, and this is 0 0. So this is not conserved, guys. Okay, and so we can see. So what we see is, right, this chart, by this chart, very important chart. I told you that here. If weak interaction is when isospin and I3 component of I3 component third component of isospin are not conserved, that then that reaction is going to be weak. Okay, if isospin is not conserved, I3 is conserved, then it is going to be EM, right? For this, all should be conserved, right? So for here you can see that isospin and I3 component shouldn't be shouldn't that they should not be conserved, right? And delta S value should be 0 or plus minus 1. So in this reaction, if you see, we can see I3 is not conserved, but I is showing conserved. Okay, so in case of I, it may be conserved or may not be conserved for weak reaction, right? It's okay, guys. If it's conserved or not conserved, it's okay. But I3 is not conserved, so it means, and it will check strangeness as well. Okay, strangeness. Strangeness, it's a 0 because no strange particle. This is 0, this is also 0, and this is also 0, right? So strangeness, we can see delta S is also 0. So it is a weak interaction, guys. What condition we have read for weak condition? That I and I3 both shouldn't be conserved, right? But here what we can see I is conserved, I3 is not conserved, I is conserved, right? If I is conserved, that is okay, guys, but I3 should be not conserved, okay? And delta S value should be either 0 or plus minus 1. So it's a weak interaction, guys, okay? Weak interaction. Weak interaction. So it is made of weak interaction, okay? This is the answer. And also by trick, I told you trick is here. If in the reaction, if you get mu e, neutrino or anti-neutrino, if reaction is allowed, then this is by weak interaction. Weak interaction. I hope, guys, you have understood. And this chart is very important for checking whether it's a this one, whether it's a this reaction is made by strong electromagnetic or weak, okay? This is the one. Next is, guys, next question. Solving the question, okay? 5 minus proton, sigma plus, and K minus cation, okay? So we'll check first. So we have to check this reaction is allowed or not, okay? For checking the reaction, whether reaction is allowed or not, we check only 4 things, guys. Baryon number, okay? Charge, baryon number, and we don't need to check isospin and spin, okay? Charge, baryon number, and lepton number, and this one, and strangeness. These 4 we need to check, guys, okay? If these 4 are satisfied, conserved, then this reaction is allowed or not. We need to check whether it's allowed or not, okay? Allowed or not. This is what we have. This is what this is asking, okay? Okay. So we are checking that first charge, okay? Charge Q minus 1 plus 1, okay? And this is plus 1 minus 1, okay? This is 0, that is conserved, okay? Now lepton number. Lepton, pion is not lepton, this is not lepton, this is not lepton, this is not lepton. So this is conserved. Now we'll check baryon number. Baryon. This is not baryon, this is baryon 1, this is baryon 1, this is not baryon, okay? So this is also conserved. Now we'll check S, okay? For reaction allowed or not allowed, we just check those 4 things, guys, where we don't need to check this I3 and I4, I component, isospin, and third component of isospin. That will check when we have to find whether it's made of electromagnetic interaction, weak interaction, or strong interaction, okay? So for strangeness, we are going to check. Its strangeness is 0, its strangeness is 0. I have already told the formula, so you can check it, okay? And for this, for lambda plus, strangeness is minus 1, and for this, strangeness is minus 1. So here we can see these are conserved. For this should be delta should be delta S should be, for being allowed, delta S should be 0 or plus minus 1. But here we can see delta value is plus minus 2, right? Because this is a plus minus 2, so this means, and this is not possible, right? So reaction is not allowed. So this reaction is not allowed, implies reaction is not allowed, okay? Next question. Next question is, omega minus lambda naught plus K minus, okay? So this is, we'll check whether it's allowed. Okay, now we need to check, is it made of weak interaction, electromagnetic interaction, or strong interaction. Okay, so then we need to check I and I3 as well. Okay, so we'll check first Q. Charge is -1, here 0, -1. Okay, and it is conserved, equal charge. Baryon number, this is baryon 1, this is baryon 1, this is not baryon, this is conserved. Now we'll check I. So you need to practice, guys. Okay, I is then you can easily solve it. I is 0 for this, because only this is singlet. Okay, 0 and 0, and this is 1/2 for I, 1/2. And if you talk about I3, this is 0, 0, and this is -1/2. This is not allowed, this is not allowed, right? This is not conserved, this is not conserved. You can see I3 and I and I3 is not conserved. Now we'll check S, strange number. This is -3 for this omega minus. I have already solved it by using formula, that is Gelman-Nishijima formula. So this is -1 and this is -1, right? So here you can see delta is going to, for this delta should be 0 or ±1 for weak interaction, right? So so you can see this is going to be, okay, so this comes like this. Okay, so this is going to be, this delta S value is ±1, right? So right, this means this is by weak interaction. I have shown you this chart, right? This one. Okay, if this for weak interaction, I3 shouldn't be conserved, and I and I3 shouldn't be conserved, right? And delta S value should be either 0 or ±1. So here you can check. These are not conserved, and this value is ±1, right? So this is by weak interaction. Okay, very good question. Next. Next is which of the following reaction, okay, is not allowed. Okay, so there is one thing. So there is a question. We need to check whether the reaction is allowed or not. Okay, mu E bar is given plus E, that is N plus E plus. Okay, so we'll check first charge. Charge is 0, 1, 0, and 1, right? And then we'll check lepton number. This is lepton 1, and this is not lepton 0, this is not lepton, this is lepton. Okay, but this is -1. Why? This is antineutrino -1. This is antiparticle of electron, right? -1. This is conserved, this is conserved. Okay, now we will check I. We don't need to check I, so we'll check baryon number. We just need to find whether it's allowed or not. Okay, baryon number. Baryon number is simple, that is 0, 1, 1, 0, conserved, right? And then we'll check strangeness. This is 0, 0, 0, 0, right? So delta is equal to 0, and these are allowed, right? Conserved means reaction is allowed. Okay, reaction is allowed. For reaction to be allowed or not, we just have to check four things, guys. I'm telling you: Q, charge, lepton number, baryon number, and strangeness. Okay, right? And strangeness should be this one, either 0 or ±1. Okay, so it's a 0. Okay, if this is the case, we just need to check Q, L, B, and S. Okay, strangeness. So this reaction is allowed, guys. Okay, this is a very important. Q, L, B, S we need to check. Okay, next question is, we have pi minus equal to electron plus pi naught plus mu. Okay, So now okay, so we need to check whether this reaction is allowed or not. Okay, simple. We'll check Q first. Q charge, right? This is -1, this is -1, this is 0, and this is 0, means this is conserved. Now we'll check lepton number. Lepton number, this is not lepton, guys. Okay, so this is 0. I have explained in detail how to check a lepton and meson, everything in chart. Okay, so if you will see my complete lecture, you will be able to understand it completely. Okay, so L is, we'll check L is 0 here. Okay, and here this is lepton number. Okay, this is lepton. Electron is lepton 1. Okay, and this is 1 and this is lepton. So you can see this is not conserved, guys. Okay, L is not conserved, so that implies this reaction is not allowed. Reaction is not allowed. Okay, well, this is the one. So guys, just wanted to tell you that I'm going to complete particle physics either in 1 or 2 lectures today. Okay, this is a Sunday special class, and then particle physics is going to be completed. Okay, in 1 lecture or 2 lecture. Okay, next is, okay, so this is the one. Next is next question, guys. Okay, next question. Next question is pi minus plus p is n plus k plus and k minus. Okay, this is the one. So we need to check this is okay, we need to check whether this equation is made of electromagnetic interaction, weak interaction, or that strong interaction. Okay, so we'll check first. Q charge is -1, and then 1, for proton charge is 1, right? Proton charge is 1, and this is 0, 1, and -1. This is conserved. Now we'll find lepton number. This is not lepton, and I have explained, guys, in detail this one. This chart is very important, then you would be able to understand these particles. I can show you again this chart. So it's a long lecture. It is going to be around 3 hours lecture, and complete particle physics is going to be completed. Okay, so this chart is very important. I have explained, so you need to know this chart. If you know this chart, you can easily solve these questions. Okay, and I have explained. I would suggest you, if you haven't watched my lecture, so watched in detail from the first. Okay, well, okay, so lepton number is L. L is going, this is not lepton 0, this is not lepton 0, this is not lepton, this is not lepton, so this is conserved. Now baryon number, pi is not baryon, it is baryon, it is baryon, it is not baryon, it's not baryon, this is conserved. Now we'll find I we are going to find, so I, this is isospin. Okay, I, this is 1, and this is half, this is 1, this is half. Okay, this is half, and this is half, so this is not conserved. Now I3 we are going to find I3 is, this is -1. I have told you how to find I and I3. Okay, you need to check it in detail. Okay, so this is 1 by 2, this is -1 by 2, 1 by 2, -1 by 2. So this is, you can see, this is conserved. Okay, this is conserved. And if you talk about strangeness, S, this is 0, 0, 0, 1, and -1. So this is also conserved, guys. Okay, so means delta S value is 0, right? So this means, so here we just need to check whether so in this question we don't need to check anything. We just need to check this one, whether this reaction is allowed or not. I have already told, for reaction to be, to check, for checking reaction to be allowed or not, we just need to check 4 things: Q, L, V, S. That's all. So here QLBS we have checked and they are conserved, right? So this reaction is allowed. We don't need to check I and I3. Okay. Well, this is allowed, guys. For if you check if in question it is asked that it is by which interaction, so you can see that this is not allowed, this is allowed, right? So this comes in this category, means electromagnetic reaction, electromagnetic interaction, right? This chart I have told you, this is very important chart. Yeah, for a strong interaction, these all should be conserved. For electromagnetic interaction, isospin shouldn't be conserved and everything should be conserved. For weak interaction, isospin and spin shouldn't be conserved, right? This chart. Well, so next question. Next question is, I'm solving lots of questions, guys, okay, and very important questions. Okay, so this is, and I would also like to inform you that in next Sunday I'm going to teach nuclear and nuclear physics, and in 2 Sundays or 3 Sundays I'm going to complete that. Okay, so in Sunday special I'm going to complete nuclear physics, particle physics, and the digital electronics and atomic and molecular physics. So I'm going to complete all your courses, all 9 subjects before the exam. The exam may be on 27th of June. So before 25th of June, I'm going to complete all the 9 subjects. Okay. Well, so the question is, mu minus equal to electron plus neutrino bar, that is antiparticle. Okay, and mu. Okay, so this is the one. So we need to check whether reaction is allowed or not. Okay, so we have to check 4 things. Okay, first we'll check charge. Charge is -1, -1, 0, 0, means conserved. Now we'll check L mu, right? Lepton number for mu. So this is 1 and this is 0. This is 0. This is 1. So this is conserved. Now we'll check Le, lepton number Le for electron, right? This is 0. This is 1. And this is -1 antineutrino, and this is 0, means this is also conserved. Now we'll check that baryon number. So this is 0, this is not baryon, this is not baryon, this is not baryon, this is not baryon, this is allowed. Now we'll check S, strangeness. This is 0, these are not strange particles, 0, right? So this is, so it means delta S equal to 0. So this reaction is allowed. You just need to check these 4 things. Okay, allowed. Reaction is allowed. Next, okay, next is next question, very good question, guys. A minus proton, that is sigma minus plus pi plus. Okay, we need to check whether which interaction, okay, it is made of electromagnetic interaction, weak interaction, or that one is strong interaction. Okay, so first we'll check charge Q. You can see -1 plus 1, -1 plus 1, and this is -1 plus 1, right? This is conserved. Now we'll check lepton number. This is not lepton, this is not lepton, this is not lepton, this is not lepton. So this is conserved. Now we'll check baryon number. Baryon, this is 0. This is a baryon, this is 0. This is a baryon actually. In chart, this is a baryon, this is 0. So this is conserved. Okay, now we have to check isospin. Okay, isospin, this step is very important, guys. So I'm going to write by that. Understand it. Okay. So if you check the isospin, this is half. Okay, this is half. Okay, for ion, and this is 1 and this is 1. So if we check this, means they are not equal, right? So this is not conserved, but it is conserved. Now if this case, if we have this case, right, so what we are going to do, we'll get their mod, means like this: 1 plus 2, 1 plus 2 mod 2, 1 plus 2 minus 1 by mod, and these values we need to check. Okay, so if we check this value is going to be this one: 1 by 2 minus 1 by 2, that is 0, 1 by 2 plus 1 by 2, that is 1. So these values are 1 and 0. Similarly, this one: 1 plus 1 2, 1 minus 1 0. So this value is going to be this one, from 1 plus 1 mod to 1 minus 1 mod, right? So this is 2 and this is 1 and this is 0, right? These values. So this, if you get this one, this is very important step, guys. You need to note down. Okay, this is going to be 2 0 and 1. Okay, the mod. So here you can see this is matching, this is matching, these two matching, means it's okay. Either if anyone is matching, means this is conserved, guys. Okay, this step is very important and you need to understand it. Okay, very important step. Two hours are completed, guys. Okay, so I hope I will be able to complete the classical this particle physics in 3 hours, I believe. Okay, so this is this I equal to this. So means this is conserved, guys. Okay, next we are going to find strangeness, right? This one, I3 component. I3 is very simple. So this is 0 0. Okay, 0 0. I3 0 0. Okay, and this is minus 1 and 1. So I3 is conserved. Okay, now we'll find strangeness S. This is 0 0. I have told you, I have explained how to find strangeness I, everything I3. Okay, 1 1. Okay, so you can see delta value is it is coming 0, right? Plus minus 0, right? So it means all are conserved, right? So means this reaction is made of is by made by strong interaction. Okay, if you will see my, if you will watch my complete lecture, I'm sure, guys, you can solve any question of the particle physics easily, because it's a detailed course and it's a Sunday special class, and I'm going to complete particle physics today. Okay, well, so this is the question. Next question. Next question is, this one is sigma plus proton plus pi naught. Okay, so we need to find uh, whether it is made of strong interaction, weak interaction, or electromagnetic interaction. Okay, so first we'll find Q. Q is 1 1 0, conserved charge. Okay, Q is charge. L, lepton number. This is 0, this is not lepton, this is 0, this is 0. Okay, baryon number, this is baryon. I have explained that in my chart. Okay, so you need to understand this, you need to memorize the chart which I have made for you. Okay, that chart is very important. Okay, so so this is 1 and this is 1 baryon number, these are baryon, this is not baryon, so this is also conserved. Okay, now we'll check I, if we check I, so you can see I is 1 for this, and this is half, and this is 1. Okay, and now what we are going to here, I already told you this step here, right? So we'll do this one: mod of 1 by 2 plus 1 to mod of 1 by 2 minus 1, right? These values. So this is 1 by 2 plus 1 is 1 by 2. This is going to be 1 by 2 and 3 by 2, right? 1 by 2, 3 by 2, 1 by 2, 3 by 2. Okay, this is 1 by 2, 3 by 2. So you can see this value, these values are not matching, so I is not conserved, guys. Okay, now we'll find I3. I3 is 1, and this is half, and this is 0. This is also not conserved. So I3 and I are not conserved, and delta S is also, delta S we can find out for this. Okay, so this is a weak interaction. Delta S we can find out, right? This is -1, and this is 0, and this is 0, right? So delta S is plus -1, right? So this is weak interaction. This reaction is made by a weak interaction, guys. Next question, guys. This is asked in GATE 2010. Okay. GATE 2010. Okay, so this question is first, pi plus is mu plus mu. Okay, second reaction is pi gamma plus gamma. Okay, third reaction is pi naught plus n, pi minus plus pi. Okay, A, B options are given, A, B, C. This is strong interaction, electromagnetic interaction, and weak interaction. Okay, so I have already told you the trick. Okay, you can check. I have already told you the trick. If you see gamma in the reaction, that is electromagnetic, that is made of electromagnetic interaction. Okay, if you see neutrino or antineutrino, that is made of weak interaction. Okay, and obviously then this is going to be going for the strong interaction. And also if you get baryon, like proton, okay, proton, neutron, any baryon, then this is going to this is for that reaction is made of strong interaction. Okay, I have already told you the trick and wrote it for you. You can check. Okay, earlier I have done that in the same lecture. Okay, next question. Next question is pi plus mu plus mu. Okay, neutrino. So we have to check that whether it is made of weak interaction, electromagnetic interaction, or strong interaction. Okay, so we'll check Q, charge +1, +1, 0, conserved. Lepton number 0, 0. Okay, so this is the antiparticle of mu minus, right? Muon. So this is -1. So this is conserved. Now baryon number. Baryon number is, this is not baryon, this is not baryon, this is not baryon. Conserved. Okay. I we are going to find 1, 0, 0. Okay. This is not conserved. I3 1, 0, 0. Okay. This is also not conserved. So this is not conserved means it's a weak interaction. By weak interaction. Weak interaction. And S is also, guys, you check 0, 0. These are not strange particle, right? So delta S is 0. So weak interaction, guys. Okay. Weak interaction. Next. Next question. Okay. Next question is pi 0, equal to gamma plus gamma. Okay, so we have to check. So we'll check Q 0 0 0 conserved. Okay, and gamma is gamma. So this I told you the trick. Gamma is there, means that is electromagnetic interaction, but we'll solve it properly. Okay, so that is then baryon number 0 0 0, I component. Lepton number is, yeah, lepton number is 0 0 0. And then I is 1. I have told you how to find is. Okay, I3. That's why I'm writing quickly now. This is 0 and this is I3 0 0 0, right? So you can see this is I is not allowed, I is not conserved, but I3 is conserved, right? So this means this is EM interaction. By trick also, I have already written a trick for you. You can check. Okay, so AM interaction. Okay, this is made of electromagnetic interaction. Okay, S also you can find out. S is 0 0 0. Okay, so delta S equal to 0. Next, guys, next question is pi plus n pi minus n proton. Okay, so we have to check whether it is by electromagnetic interaction, weak interaction, or strong interaction. Okay, so first we'll get check, that is so we can also do it by trick means pions are here, right? This baryon, so it is by strong interaction, but I'm going to solve it with procedure. Okay, 0 0 minus 1 plus 1 conserved Q charge. Okay, lepton number 0 1, sorry, 0 0, this is 0 0 0, this is conserved. Baryon number, baryon, lepton number, everything I have explained in detail. That's why I'm writing quickly now. Okay, B is 0 1 0 1 conserved. And now I is important. Okay, I is 1 1 by 2 and 1 1 by 2, guys. Okay, so this is conserved. I3 1 minus 1 by 2. I have already explained that, solve many questions of how to solve I3S. Okay, you can check that. I3 is 1 by 2 minus 1 1 by 2 conserved. And strangeness 0 0 0 0, this is conserved. So all are conserved, right? Means all conserved, and delta is equal to 0, means strong interaction. Strong interaction. Okay, these are the question, and now we are going to study this quark composition, very important. Quark composition. Okay, quark composition. Okay, so what is quark? So hadron, hadrons, combination of quark particles. Okay, hadron are combinations of quark particles. Okay, and they don't exist, they don't exist in the free space. They don't exist in free space. Always found in composition. Okay, so hadron, it's a combination of quark particles. Okay, so they don't exist. These quark particles don't exist in free space. Always found in composition. Okay, so I'll explain those things as well. So now this is up. Okay, up. This is the quark composition denoted by U. Okay, up and down. This is one category of quark. Okay, and this is doublet. This is denoted by down is denoted by D, and these are doublet. Okay, doublet. So from here, doublet means we find 2I plus 1 equal to multiplicity is 2. So from here, I is going to be 1 by 2. Okay, and for up, that is U, I3 is going to be 1 by 2, and for down D, I3 is going to be minus 1 by 2. Okay, I have already told this formula, guys. Okay, now for charm, for charm, for charm, for charm C, this is singlet, guys. Okay, singlet. So I is I3 is 0 because 2I plus 1 equal to 2I plus 1 equal to 1, right? 1 1 will get cancelled. I value is going to be 0. So I3 and I is 1 for charm because it's a singlet. Bottom, next bottom, bottom, bottom B, it's also singlet, singlet. Okay, so for this also I and I3 equal to 0. Now for top, these are quark particles. Okay, which is denoted by T, and that is for this is also singlet, singlet, right? So I equal to I3 equal to 0. Okay, next is strange particle, strange quark, strange. This is also singlet denoted by S. Okay, strange S, and right, and for this I equal to I3 equal to 0. Next, now I'll tell you one procedure. Okay, this is, you can write this trick. Okay, very important. If you write cut, 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 for cut, that charge is going to be 2 by 3 electron. Okay, cut means C tends to charm, for quark. Okay, U is up for up particle and T is top. Okay, so for the cut means with this charge Q is 2 by E. Okay, and for BDS charge equal to minus 1 by minus 1 by minus 1 by 3 electron. Okay, and BDS means B bottom. This is a trick, guys. Okay, D down and S strange. Okay, S is strange, right? So this is important, the charge part, so you can easily remember it. Okay, cut means charm up and top. This charge is going to be 2 by 3. For BDS, this bottom, down and strange, this this is Q is minus 1 by 3. Okay, now I'll make a chart. So chart is this one, guys. U, D, S, C, T and D. Okay, so U for up. These are quark particles. Okay, 6 particle up, down, strange, charm, top and bottom. Okay, so now we are going to find, so first we are going to find baryon number. Okay, baryon number for charm is up is 1 by 3, down 1 by 3, 1 by 3, 1 by 3, 1 by 3, 1 by 3. That is the baryon number. Okay, and I, that is isospin, for up 1 by 2, for down minus 1 by 2, just 1 by 2, and for others 0, 0, 0. And if you talk about I3, for up 1 by 2, this is minus 1 by 2, remaining are 0, 0, 0. Important chart. Now charge for up 2 by 3, I have already told this chart, right? BDS and cut. So this is 2 by 3, this is for down 1 by 3, for strange 1 by 3, and for cut the charm 2 by 3, and for top 2 by 3, and for D minus 1 by 3. So you can also understand like this, guys.